Hi guys, so in trim and static stability so far we've introduced the concept of stability, i.e. how the aircraft is perturbed from a trim state and what's its tendency to return, and we introduced the concept of stability derivatives. So we've expressed these in non-dimensional forms, and we're going to talk, so what we looked at in the last couple of lectures were the important pitch stiffness derivatives, CL alpha, and how we can relate that to things like CG position. And then we spoke about pitch damping, understanding that CLQ is always going to be a restorative term, but we don't really have a means of determining its actual value yet. So in real life aerodynamics or in real life sort of aircraft development, the derivatives will be estimated numerically using a suite of computational packages, starting with sort of basic well, not even computational, starting with some empirical and maybe some Excel calculations, or you'd use Python if you want to stay away from Excel. You do some calculations based on some of the theory that we're going to just do a quick intro to in this lecture. We then use potential calculations to look at including things like induced aerodynamic effects and potentially looking onto using computational fluid dynamics to get better estimates of the stability derivatives. They'd then be evaluated in a wind tunnel experiment as well, and that's what I spent a lot of my job doing, working at the old wind factory. I used to have wind tunnel models in the tunnel, and then we move them through a suite of rates and aerodynamic angles to look at the variations of force, and therefore forces and moments, and then go through a whole series of non-dimensionalization to turn them back into the non-dimensional stability derivatives. So what I want you guys to be able to do in this course is not necessarily do the actual numerical estimation of them. I want you guys to have an appreciation of the numerical estimation, but the full process is very, very involved. And for what is a small part of a big course, I'm not expecting you guys to have a full, complete understanding. But if you've got any questions on it, please let me know, and I'll hopefully include more detail on the website. What I want you guys to be able to do is just have an appreciation of how that process is performed, and also to be able to intuit some characteristics about the aircraft. So we're going to look at development of the roll damping derivative and how, also CLP, and how we can, or how we could perform a simple estimate of the roll damping derivative. We're going to also look at how we can include some other cross-coupling terms, so i.e. if the aircraft starts to yaw, what is the effect on roll, and can we think about where these effects come from the different aerodynamic surfaces. And we're going to have a small look at gyroscopic precession. So all aircraft that are built have got a bloody great gyroscope in them. That is the engine. The engine is a big spinning mass, so it's a mass that has both a rotation vector and a moment of inertia, so it has a big angular momentum, and if we try and move that angular momentum, then because of cross-coupling effects, because of gyroscopic precession, the aircraft will want to move in a different axis. So that gives us cross-coupling in our pitching and yawing motion. So we're going to talk about that today, and how we can use a handy sort of right-hand tool to help us remember the sign conventions there. So let's have a look at, firstly, a numerical estimate of roll damping. And I've put here it's a numerical estimate. We're actually not going to come up with a number at the end of this. We're just going to come up with a relationship. So I maybe should just put an estimate of roll damping. So we've gone through a lot of non-dimensionalization in this course so far, and we've looked at estimating things like the aircraft pitching moment coefficients, remembering that the pitching moment coefficient is equal to the pitching moments divided by a half rho v squared s. And then the characteristic length for pitching motion is the the mean aerodynamic chord. So we've got this non-dimensional representation of pitching moments, and we said that Cm is equal to Cm naught plus Cm alpha multiplied by alpha plus Cm q multiplied by q plus Cm dE dE. So all of these terms are non-dimensional when in this expression. So the product of all of these are non-dimensional. But the actual side or the units of the derivatives themselves are not non-dimensional. So the units of this would be 1 over radians. The units of alpha is going to be radians. The units of cmq is 1 over radians per second. And the units of q are going to be radians per second. So you will often see in different texts and used more commonly, and what we're going to use today are some non-dimensional angular rates. So because our angular rates have got the units of radians per second, we will convert to non-dimensional angular rates because it removes a lot of components to different equations. So non-dimensional and I have to refer back to my notes just to check I get this correct here. So we have these dimensionless roll, pitch, and yaw rates, and the way that we define them is we think we need to multiply them by something that's going to get rid of all of the units. So our pitch, so P, Q, and R, those are our non-dimensional roll, pitch, and yaw rates. And the way that we define these, we take our pitch rate, we multiply it by the wingspan, and we divide it by 2 multiplied by the dynamic, or the incoming velocity. We have similar expressions for the other two. So the roll rate also has the yaw rate also has the span as the characteristic length. And just to mess things up, the pitch rate has P C bar and 2V infinity. And this just helps us because think about where we're using these expressions. We're going to use the pitch rate in the pitching expression where we need to have an extra C bar when we're collecting terms. By contrast, when we're looking at the others, we've got, say, CL, the non-dimensional rolling moment coefficient. That's equal to L divided by half rho V squared S B. So we keep the divisors in both the coefficient form and then in these non-dimensional angular rates constant, and they help us remove some terms from each of these equations. So we're going to look at how we can estimate the roll damping derivative. So the roll damping derivative we're going to say is CL Q bar. Okay, so CL Q bar is defined as the rate of change of CL over Q bar. Put the partial derivatives there right there. Okay, so we've got rolling moment coefficients. And we've got non-dimensional. I fucked up here, haven't I? I'm gonna edit this, go back. Okay, roll damping derivative needs to be CL, and it's going to be P is the roll rate. So CL P, but instead of P, we're going to use P bar. So CL P bar is equal to the partial derivative of CL divided by the partial derivative of CL with respect to P bar. So let's just remember what these two are. CL is the roll moment coefficients. And then P bar is this non-dimensional roll rates. And then we can remember that P bar is equal to the dimensional roll rate, which has got units of radians per second, multiplied by C. So in this case, it's multiplied by B divided by 2 times the velocity. Okay, so we're going to look at how we can estimate this roll damping derivative. So roll damping, we've said before, as the aircraft spins around, it's got a roll rate P, or a non-dimensional roll rate P bar. That's going to cause damping largely due to the wings. So we're going to have a look at how we can estimate what that damping is going to be proportional to. So we're going to use a simple rectangular wing to help us understand really what this effect can do. So we've got a rectangular wing. So it has constant chord of C. It's got span of B. Let's say this is my aircraft longitudinal axis. So that's denotes our flight speed, V infinity. And then using the right hand rule, we've got effectively our starboard side, which is on the left of the page, would be down. We've got this roll rate Q. Sorry, roll rate P. What am I talking about? Okay, so what this is going to cause on the wing, it's going to cause an upwash over here and a downwash here. If we're not certain about that, let's just remember that if we looked at this aircraft from the front, we've got a wing here, this aircraft is rolling with roll rate P, then there's going to be a velocity field that is proportional to both the position along the wing and the roll rate. Okay, so this is just from the motion of the wing itself. So if we take a section of this wing, let's say take through here, then let's just remember our coordinate system. The only ordinate we really care about here is y, so it doesn't matter about our vertical position of the axis. So we could have a look at the two-dimensional cross-section through here. We'd say we've got a wing section, so we've got an aerofoil, we've got V infinity, and we've then got this upwash, and the upwash has the magnitude y multiplied by P. And this is true whether we're on the port side or the starboard side, because we've got positive y in this direction and we've got negative y on the port side. So on the port side we've got a negative velocity going up, so that then gives us the correct sign here. So what we get because of these, we have an effective angle of attack, which we call alpha prime here. So alpha prime causes an increase in the lift, which this is where we're going to get a little bit confusing. I'm just going to say dc, and I'm going to put uppercase L for the change in the lift coefficient, but this is actually the elemental change in the lift coefficient, so I should put a lowercase l, but I don't want to confuse it with the rolling moment. This is the change in the lift per span. So we can work out this alpha, what it's equal to. Alpha prime is equal to the arctangent of yp divided by v infinity, which for small angles is approximately equal to yp on v infinity. So the arctangent, small angle approximation, we don't tend to use that so much, but I did a quick check because I wasn't certain about it myself how valid it was. Let me just show you on here. So again, I wasn't certain about the validity of the arctangent myself, so I just did a quick bit in Jupyter. Let me make this smaller on the screen. Okay, so if I'm not sure about something, I try and do a little numerical approximation to see what's going on. What I'm plotting here, and I haven't even put axes labels on, I've got angles in degrees. I've got the two, so I've got both the proper arc tangent and the small angle approximation, and then I've got the percentage error in the approximation. So you can see that even for angles up to about 20 degrees, the relative error is actually only 5% in the small angle approximation. So you'll see these small angles being used. You should be comfortable with sort of just testing them numerically and seeing what the approximations mean. But we've got this, we've now got this expression for the change in the angle of attack at the section. So let's see what this is. This is change in sectional alpha due to that roll rate P. So we've got that, and we can then, if we know the lift curve slope of the wing, then we can determine the change in the actual lift. So let's say that dCl is equal to AW multiplied by alpha prime, which is equal to AW multiplied by the expression that we just developed. So that's Y P on V infinity. This is change in sectional lift coefficient. I'm just writing that down because if we have a CL at this stage, we need to be certain whether we're talking about lift coefficients or whether we're talking about the rolling moments. So we can then now look at the actual dimensional value of the lift this would produce, and I'm going to call this D lift because I don't want to call it DL, even though that would be correct because L uppercase is going to be our rolling moment. So I'm just going to call it D lift for this time being. We take this expression and we then multiply it by the dynamic pressure and the chord. So it's going to be AW YP V infinity multiplied by Q infinity C here. Okay. So this is then our expression for the change in lift, and then if we've got this change in lift, then we can think about the moment that that's going to produce. So if we've got positive lift, then it's going to make us have a moment that is clockwise when viewed from front, so that's a negative moment. It's a moment that's produced by this distance y. So the combination of those two gives us our change in the rolling moment due to the roll rate because of the upwash or downwash on those two wings. So we can write that now. dl is equal to minus the y, which is the distance along the wingspan, multiplied by the expression that we've just written above. And let's be really clear about this. This is the change in sectional contribution to the whole aircraft rolling moment in this case. So that's the change in the positive rolling moment due to the lift produced at some position y. Okay, and this is valid for both the port and the starboard wing because the sign of y changes, and that is present in both here and here, and that's going to then change the whole expression to give us the correct sign on the moments. So we can then integrate this expression to get the whole rolling moment. And the limits of the integration is going to be from one wingtip to the other. So for us, that's going to be equal to minus, because we've got a minus sign in the expression above, b on 2 to minus b on 2. And let's just simplify this expression. We'll collect the y's together. So we've got AW y squared, p on v infinity, q infinity, C dy. Okay, so if we perform this integration and put the limits in, then we get L is equal to minus AW b to the 3 divided by 12 P on V infinity Q infinity C. Okay. And we can see here that the moment induced by a positive roll rate is a negative moment. And that's good for us. Let me make sure my camera is flipped around so I'm not doing this back to front. Stick my right hand out through the aircraft, then the aircraft x-axis, and my fingers curl around, giving it a starboard wing down roll rate. Starboard wing down roll rate means I've got more lift being produced here, and I've got less lift being produced here. So this gives me a more lift here, effectively less lift here. I've then got a moment that's restorative, which is a negative moment. Okay, so the sign of this makes sense, and it shows us that we haven't messed up in our algebra or our calculus. So we want the coefficient form. So we'll say that, or we'll just remember that CL, which is our rolling moment coefficient, RMC, rolling moment coefficient, is equal to the lift divided by half rho V squared SC. So let's just remember that S for a rectangular wing, which is what we're working with, is equal to B multiplied by C. So if we divide the above expression by this, then let's look at what's going to disappear. Well, there's a whole bunch of things that are going to go. We've got dynamic pressure in here. We've got S, which is BC, so we get rid of one of the terms up here. We've got, what else have we got? We've got C, which goes as well. That's good, I think. So we end up with, am I missing a term here? Let me just check. No, the mistake I made is, because I've been stupid, the definition of the rolling moment is not with a C at the bottom, it's with a B. Okay, and that's why. Because then when we do this through, otherwise we would have had an extra C. So that C up here cancels because of this C. And then we've effectively got B squared, so this just disappears up here. So our expression then becomes CL is equal to minus AW B multiplied by P divided by 12 V infinity. So this is the rolling moments coefficient due to roll rates, P, which is still at this moment the dimensional roll rates. And if we look what we have here, we've got B, P on V. And we remember from the definition of the non-dimensional roll rate, the P bar was equal to B, let's make that a lowercase p bar just to be consistent. P bar is equal to B, P to V infinity. So we split the 12 into 2 times 6 and we end up with CL is equal to minus AW on 12 P bar, not 12, on 6 rather. And then we can see that CLP is equal to the first derivative of CL with respect to P bar, which is simply AW on 6. Okay, so we've now got an expression for our rolling moments damping. So this is roll damping, so this is the change in the roll damping due to, change in the rolling moment due to a roll rate, and what it's a function of here is just the wing lift curve slope. So we've said here that the non-dimensional roll damping, just to take the wing lift curve slope divided by 6, and then we've got the negative value of that. So we've always got this negative roll damping. We can compare this to a slightly more complex example. Now, this is still a really simple example that we've done. So the assumptions that we had here were rectangular wing, no induced effects, no sweep, and so by virtue of it being a rectangular wing, there's no taper, so the taper ratio is just 1 on this wing. We can, if you want to look at a more detailed discussion of this, I would advise you to look at McCormick's Aerodynamics, Aeronautics and Flight Mechanics. But if we just look at the expression that he goes through and looks at a tapered wing, and so for a tapered wing, what he develops is and remember, for a tapered wing with no sweep, wing looks something like this. Let's try and draw that more symmetric. So we have a tip chord and a root chord. So the taper ratio is defined as the tip chord on the root chord. So McCormick gives for CLP bar is equal to minus A0 on 12 multiplied by 1 plus 3 lambda on 1 plus lambda. So this is for a tapered wing. The only difference with doing this for a tapered wing is that in the integration here, c is a function of y here. Okay, it's just a geometric function, so it's not particularly difficult to do, but it would just have added an extra complexity here that I didn't want to go through. But we can see that if you set lambda equal to 1, then what we end up with here is 1 plus 3, which is 4 over 2. So it's taking this expression, multiplying the whole thing by 2, and we end up with this here. Okay, so we've gone through a simple estimation of the roll damping derivative, and we've introduced this idea of the non-dimensional roll rate to help us work this out, because you'll see this and you'll see these non-dimensional derivatives more and more when we actually end up developing them. These derivatives themselves are just numbers then. They're numbers that we work out, and we use them to help us determine how different aircraft perform compared to another. And like I like to say, they are effectively the soul of the aircraft, how it wants to move in the sky and how it's going to respond to perturbances. So we're going to have a quick look at cross-coupling as well. So everything we've done so far, including this roll damping, is sort of looking at a single axis, what one axis does on another. We can intuit using some good reasoning. Maybe not intuit, we can evaluate and we can consider and we can work out what the effect of cross-coupling is. So by cross-coupling, this is the effect on one axis due to motion about another. And we're going to look at two different forms. We're going to look at the aerodynamic cross-coupling, largely due to the vertical tail we're going to look at. We can look a little bit due to the wings as well. And we can look at the effects due to having a gyroscope on the aircraft. So we've got if we have a propeller or a big gas turbine engine, this induces gyroscopic precession. It brings in gyroscopic precession, which causes an off-axis motion that is somewhat counterintuitive. And there's also another aerodynamic force that's a cross-coupling that occurs due to propulsion itself. If we have a propeller on our aircraft, then we have aerodynamic effects that cause these stability derivatives to have some cross-coupling. So let's have a think about what these cross-couplings could be and where they come from. And I'm going to come up with a very simple example at the beginning. We're going to look at the effect of yaw on roll. Okay, so we're looking at the effect. If we are having a yawing motion, what's going to happen to the roll attitude or the roll rate of the aircraft? So we're looking at the effective yaw motion on aircraft roll. So you remember yaw motion, which one's that? Well, X, Y, Z, so it's going to be P, Q, R. So R is our roll rate. Okay, that's our roll rates. Sorry, our yaw rates. And then we're going to look at the effect on the aircraft roll. So we're going to see what induces us a rolling moment, L. I realised when I went through PQR, I sounded really stupid. I'm trying to highlight to you guys that you can always work out which one of these is which. Just remember X, Y, Z, LMN, PQR. You can always work it out. So let's think about what happens to the aircraft if we yaw it. We're going to look independently at the wings, and we're going to look at the rudder, or not so much the rudder, the vertical stabilizer, what happens. So wings. Again, we're just going to look at a simple rectangular wing. There are different effects that occur due to sweep. We're not going to look at those so much. We're not going to look at them at all, actually. Got our aircraft centre of gravity, and we're going to have a positive yawing motion. So we've got this yaw rate. Remember, thumb down. So we've got this here. It gives us our yaw rate R. Okay. And because we're just looking at the signs of these, we can work in terms of these derivatives with respect to the dimensional rates, because I don't want to bother looking at the non-dimensional, because we're not working out and doing much algebra here. We don't need to bother with the non-dimensional roll, pitch and yaw rates, because the signs of the derivatives are always going to be the same anyway, and it's the signs that determine the stability. So we can think about where this comes from here. So if our aircraft is now yawing, this effectively, we've got an increase in dynamic pressure here. We've got an increase in dynamic pressure here going the wrong way. So this is effectively the port wing is going faster, the starboard wing is now going slower, in effect. Okay, so what this does, this causes an increase in lift on the port wing and causes a decrease in lift on the starboard wing. So what's that going to do? It's going to induce a moment. So this is going to produce a plus L, and this is going to induce also, if we've got less lift on the starboard side, it's going to cause a moment that's starboard wing down a plus L rather. Where in these, this is rolling moments. So we would now expect dl on dr to be greater than 0. This is the wing contribution. And we can think about what this physically means. We've got our aircraft here. If it starts to have a positive yaw rate, so we're now going nose starboard is a positive yaw. That's actually a negative side slip, but we've got this positive yaw rates. This wing has more lift, this wing has left, we've then got this here. So our aircraft has a tendency to do this motion. If it starts to yaw, it will start to roll. Okay, that's the contribution due to the wings. There's also a contribution due to the vertical stabilizer. Vertical stabilizers here. So let's call this vertical stabilizer, or the vertical tail. Then if we've got this yaw rate, then what we have here, we have a effective sideways velocity. So we call this a plus V occurring here. We'll call it V on the tail, okay? This is the component of velocity. We've got this increase in sideways velocity. We've still got the aircraft free stream going towards it, but what we effectively have now is an effective side slip that's occurring on the tail. So what we're going to have here is a side force. Okay, and the side force is occurring on the tail, so this is going to give us this tendency to counteract the motion that causes it. So remember, this is what gives us this weathercock stability. That is DL, that's then the change in the yawing moment due to the yaw rate. That would be dn by dr. We're now interested in this effect on roll rate. So why does it induce a roll rate? Well, we look at any aircraft. Just trying to do a sort of isometric presentation of this a little bit, it's quite difficult. This is our aircraft. Let's draw our centre of gravity here. Then if we can think about where this sort of vertical tail is, the vertical centre of pressure, or the vertical aerodynamic centre, is going to be located some distance above the centre of gravity. So we'll call this LH. Because it's located a positive distance above the centre of gravity, that's going to induce a moment, or it's going to produce a moment about the roll axis, and that rolling axis is going to produce a positive moment because in this case our side force is positive towards the starboard side and we've got a positive yaw rate, so it's also going to introduce a positive roll moment. So what we're seeing here again is that the contribution due to this dl on dr, we would also expect this to be greater than 0. Exactly the same things occurring here. The aircraft has this tendency, if the aircraft has a yaw rate going nose starboard, we then see an increase in the force vector being produced by the tail. So as we go here, we've got an increase in force vector, and because this is located this distance above the centre of gravity, it's going to cause the aircraft to have a positive roll rate. Okay, so we've got the two contributions towards the derivative dl by dr. And remember, if this is the sign of these, then we would expect for both of these, we'd expect CLR to be greater than 0, and as a consequence, CLR bar to be greater than 0. Okay, we would change the actual magnitude of these derivatives if we were looking at the numerical value, but the sign of them we'd expect to be the same. And we can think about the different parts that are going to affect them. If we have a very large tail, if you're on, say, the Tornado, a very large tail is going to increase the tail contribution to CLR. So CLR, in addition to being good for getting rid of limescale on things, is the effect on roll moment due to yaw rates, and with a larger tail, it's going to be a bigger number. Again, with larger wings, it's also going to be a larger number because you've got a larger moment being induced there as well. Okay, so that's one of the cross couplings we can look at. Let's think of some others now. I'm going to leave those cross couplings there. I might ask you to consider some just from intuiting, say from the layout of the aircraft, and I want you to use your reasoning to decide what the size of these respective derivatives are, and some of them we don't have a good way of estimating using just our intuition, and we'll talk more about those in the review session on Wednesday. Let's have a look at gyroscopic precession. Gyroscopic precession is a phenomenon that's not taught very well, I don't think, a lot of the time. Gyroscopic precession is the tendency for something spinning when we try and move it, or when you apply a motion or a torque that is about an axis, it has a tendency to move in another axis. If you've ever used an angle grinder, you'll be aware of this, because if you try and move it, it will sort of want to move in a weird direction. It doesn't feel right. Or if you've ever used a circular saw, for example, circular saw spinning really fast can be bloody dangerous, because if you try and move it in one motion, it will have a tendency to do another. So we can describe this mathematically using the concept of angular momentum. And we're not going to go and do a numerical calculation, but we're going to use this because it helps us to describe things. So I will put a link in Slack to a good video, but I advise you guys to just go on YouTube and search for gyroscopic precession, because you'll see all sorts of videos. You might have had one done in high school where your science teacher held a bicycle wheel on a piece of string, span it around, and found that it was self-stabilizing, and that's because had the gravity was causing it to want to turn off axis. The gyroscopic precession turned that into a yaw instead. So because I don't have access to those things around me, I'm going to ask you guys to Google that. But let's just think about what this physically means. So if I have some spinning object, which I'm going to just put a big spinning disk here. Our convention for spin, or our convention for rotation, is to, let's say we're looking at a P. Okay, so P is our roll rate in this example. That's defined as a rotation in accordance with the right-hand rule. So fingers clasp around that. So I can't see how that's working on screen. Yeah, okay, so that's correct for this. So that's our positive roll rate here. So this object has a certain moment of inertia, and because it will have this angular vector P, we have a total angular motion vector associated with it, omega, which we draw mathematically as a vector pointing along the axis of rotation. And we have this convention that we draw it positive if the rotation is in accordance with the right-hand rule, or we draw it if it was rotating the other way. We would draw the vector going in this way. That would be our rotation vector if it were rotating in that sense. Now we draw these vectors, and it can be somewhat confusing thinking about, well, why does an arrow vector help us understand rotation? We have to just think about these arrows as just a human construct that help us understand things. Arrows don't even really mean anything in linear translation, but it's going to help us understand what happens when we try and move this object. So I said, I haven't necessarily said, but if we've got a propeller at the front of an aircraft, just like a gyroscope on the bicycle wheel, if the aircraft tries to pitch up, it will have a tendency to yaw because of that, because of gyroscopic precession. And the reason that we can describe this as being and we're going to talk more about this and this concept of angular momentum in the next module. Angular momentum is given the symbol, annoyingly, L as a vector. Okay, sometimes you'll see angular momentum being given the symbol L. We're going to give it the symbol H. Okay, it's more common in aircraft aerodynamics to give angular momentum the symbol H to avoid having another L to confuse things. But in physics, it's often given the symbol H, so just be aware of that. If we try and give this, so this would be a propeller on the front of our aircraft. We've got aircraft here, and we're sort of viewing this almost from the side. I should be really, let's say this is from here. So we're looking at the aircraft from the side. So we've got our y-axis going this way. Now this isn't the origin, but I'm just drawing where the y-axis is normal to. So if we try and pitch the aircraft up using a positive pitch rate of P, then what's going to happen to our angular momentum vector? Our angular momentum vector is now going to be tilted up in this direction. And we're going to say this is H prime. So for the conservation of angular momentum, the total angular momentum in this system has to be equal. So we join these up with a line here to make these two, which is H prime, and this, which we call delta H, have to be equal to the original, which is H bar. So we have to have some angular momentum expressed in the system. Now this is then a angular momentum vector, which I've drawn in blue. It's pointing downwards in this new aircraft rotating axis. So for here, I've got my downwards vector. This is then a nose starboard. Okay, and this is for the case where I've got an aircraft with a propeller that is clockwise when viewed from the pilot's sense. So when the pilot sees the aircraft as clockwise, a positive pitch rate, which is, called that P there, bugger, I should have called that Q, sorry. Okay, a positive pitch rate Q will cause a positive yaw rate. Or a positive yawing moment, rather. Will have an associated yaw rate. Okay, and our yaw moment, let's remember moments, L and N, so that is N. So we would expect this to then be a positive coupling, so D, N, DQ, we'd expect to be greater than 0 for a propeller that's clockwise rotating when viewed from the front, so when viewed from the pilot's view. That's only because of this rotation sense of the propeller. Let's have a look at if we had a propeller that was spinning the other way. So we're going to draw the same aircraft here. We've sort of got the pilot's view here, and we've got a dirty grey gyroscope on the front, which is the propeller. Aircraft longitudinal axis, and the pilot's now viewing this as counterclockwise rotating, which means that our angular momentum vector, H, is now pointing in this direction. Just that's the convention for angular momentum. So again, a positive pitch rate would cause the angular momentum to shift to this position, to H prime, and in order for the total angular momentum to be constant, we'd have to have this vector produced, which is this delta H, and this then thumb upwards gives us a nose port. So for a counterclockwise pilot view propeller, a positive pitch will be accompanied, it's behind my head, let's move this up, by a negative accompanied by a negative yaw moment. So we would expect for this dn on dq to be less than 0. So we've shown here there is an inertial coupling that can occur due to gyroscopic precession that is dependent on the rotation sense of your propeller, your engine, or whatever else you have on your aircraft. This can be considerable for a large propeller or for a large gas turbine engine. It's part of the reason why the turns can be asymmetric in a lot of different aircraft, because the aircraft has this tendency to want to turn in one axis when we pitch it. And there's exact same coupling between, if we try and yaw the aircraft, it will have this tendency to pitch as well. And I leave it to you guys to look at the sign convention for those. I'm going to leave those there. I was going to talk about aerodynamic couplings due to propulsion, but I'm not going to go through them actually. I'll leave those for next year's course. We're not going to go through them today. So we've gone through quite a bit. Let's just have a review of what we've covered today. Okay, so this is where we got up to at the end of the last lecture, the estimation of the neutral point. What we did in today's lecture is we had we wanted to estimate this idea of roll damping. So I introduced gave a reminder of our sort of stability derivatives and what we meant. And we had this part where we said, well, the product of stability derivatives and the quantity that we multiply them by, that product is non-dimensional, but the derivatives themselves are not. So we introduced these non-dimensional angular rates to just mess things up even more, we'll say, to give you a whole other bunch of things to remember. And then we said that, well, all of these are defined as the angular. This was a stupid mistake. I don't know why I put P in all of these. That should be Q and R there, okay? It's good that I go back and review this stuff. So here our pitch is the one that's multiplied by the mean aerodynamic chord, divided by twice the local free stream. The other two, the roll and the yaw, are multiplied instead by the wing span. So we then had a look at the roll damping derivative, and we sort of know that it's a function of the wings here. The wings are what contribute to roll damping. And we then said, well, we're going to sort of come up with a model for this non-dimensional roll damping derivative for a simple rectangular wing. We went through it, said, well, we came up with a linear expression for the change in the angle of attack along the wingspan due to this roll rate. We then integrated that, got confused between L being rolling rate and so being either rolling moment or lift, because it is confusing. So just be careful. That's why I've put all these sort of narrations about it like this. And we then came up with an expression for CLP bar, which is the rate of change of the rolling moment coefficient due to the non-dimensional roll rate. And we said, well, it's just equal to minus the wing lift curve slope divided by 6. And then we compared that to the slightly more complicated expression in the McCormick textbook and showed that for a rectangular wing, indeed, that expression holds true. We then looked at cross-coupling, which is the effect on one axis due to the motion on another. And then I said, well, we'll look at two things: yaw motion on aircraft roll. So it's this idea of aerodynamic cross-coupling. And we found that both of these, we looked at both the cross-coupling, whenever we've got yawing, the wings cause the aircraft to tend to roll, and that cross-coupling is a positive derivative. And we said the same with the vertical stabilizer. As long as that vertical stabilizer is above the center of gravity, which it normally will be, we have the same thing. We have a positive derivative here. And here I've just highlighted that the derivatives, no matter how we express them, whether it's in this dimensional form, which would be LR, or if it's in the derivative form with a dimensional rate, or whether it's in the non-dimensional derivative form, the sign is going to follow on each of these, because with the change between these forms, all that's going to change is the actual numerical value, not the sign of it. So the stability criteria are all still the same. And then I thought I'd confuse things even further by bringing up this idea of gyroscopic precession. Now, if you haven't seen a demonstration of someone holding up a bicycle wheel, spinning it round on a piece of rope, and seeing it, rather than fall down to earth, it's spinning round, I advise you heavily to go to YouTube and look up one, because you'll understand this more. And then we said, well, there's now going to be a cross-coupling. If our aircraft has a propeller at the front, or anything, gas turbine in there that's somewhere on our aircraft, if it has a tendency to pitch up, it's going to have a tendency to yaw. And we then show that the sign convention, i.e. which way it's going to yaw, is going to depend on the rotation sense of our propeller. So for a propeller that's rotating clockwise from the pilot's convention, our way of remembering this is I've got my thumb sticking out along the rotational axis. If the aircraft pitches up, to get my rotation vector h back to its original position, I've got to have a thumb going down. That's going to be a motion in that sense. So we have a motion which is this yaw rate, which is positive. So we'd expect a positive cross-coupling in pitch and yaw for a propeller that's rotating clockwise from behind. If it's the other way around, it's rotating counterclockwise when viewed from behind, then our vector goes from this sense down to here. So to get it back, we have to have a vector in this direction, which gives us a nose port rotation. So that's a negative coupling between pitch and yaw for that rotation sense of the propeller. Now, if you can see this causes this effect with propellers on aircraft, imagine the effect that this is on a helicopter, which has a bloody great gyroscope on the top. And like I say, if you've ever held a circular saw or an angle grinder, you'll sort of have an intuition for what this feels like. If you try and turn it in one direction, it wants to go in another. Okay, so we've gone to the end of this static stability module. We've introduced the ideas of trim and static stability, and we've introduced the concept of stability derivatives, and we've shown them in three different formats: dimensional, coefficient, and then the non-dimensional coefficient forms. So the way I want you guys to think about these derivatives is to be able to relate them to the stability of the aircraft. The stability, remember, is going to be if the aircraft is perturbed, does it want to go back? So we need to be able to remember that for stability in pitch, Cm alpha needs to be a negative one. Cn beta is going to be a positive quantity. That's the only case where that the sign convention changes. For all of the derivatives that are uniaxial, so the effective roll rate on roll moment, for the effect of yaw rate on yaw moment, the effect of yaw angle on, the effect of, say, pitch angle on pitch moment, we have stability given to us by a negative derivative because we've then got a restorative moment. It is just Cn beta that has that annoying convention because of the definition of the side slope term. So we introduced the things that are going to give us stability, and we introduced the neutral points being the position at which the sign changes in Cm alpha. So if the Cg is ahead of the neutral point, then we have a negative Cm alpha, and that gives us stability for our aircraft, meaning that when it pitches up, it has a tendency to pitch down. If the CG is aft of the Cm alpha, if it pitches up, it wants to pitch up even more. So it's not flyable without a flight control system, and no civilian aircraft will have a Cm alpha that is greater than 0. So the other derivatives we looked at, so we looked at cross-couplings, and I want you guys to sort of be able to intuit those just by aircraft parameters. So we expect a positive coupling between roll and yaw. So if our aircraft yaws, we showed that if the aircraft yaws positively, no starboard, then we expect a positive roll rate to be experienced because of both the wings and the vertical stabilizer. And we then looked at the effect of having anything spinning on our aircraft, introduced the change to the angular momentum vector. There's a cross-coupling that's induced in addition as well because of those. So this has been an introduction to static stability, and we've introduced the idea about how the aircraft has this tendency to return. So we've gone through and we've used some models to come up with some numbers, or we could come up with some numbers, for example, for the roll damping or for Cm alpha. We don't yet have an idea of how, there's Poppy running around with a squeaky toy, that's really helpful. We don't yet have a means to analyse the actual transient effect of the aircraft. So the aircraft, like we say, it might have this tendency to return to pitch, but it might have an oscillation that is then increasing in magnitude. That would be an unstable pitch mode. So in order to analyse the transient effect of the aircraft, we need to develop the full aircraft equations of motion. We can then have a little look at those and their non-linear forms, how we can express the time variation of them. But to look at stability, we really need to have some linear expressions, so we'll linearize them. We'll develop the characteristic equation of the two main branches of motion, so that's longitudinal and lateral directional, and we're going to separate the eigenvalues from that system into characteristic modes of motion. Okay, so that's the end of static stability. We'll be moving on with developing the aircraft equations of motion over the next few lectures.